Hello, hi to everyone. In this video, we will discuss frequency transformation in the analog domain. Okay. In the previous videos, we have discussed how to design the analog filters such as low pass, high pass, and band stop. Right. So we have two techniques in order to design the filters in the analog domain. First one is Butterworth filter, second one is Chebyshev filter, right? So we can design by using those two methods, we can possible to design the filters. But here, so we have only the specifications, any one of the specifications. For example, here we have low pass filter specifications. Okay, so here we have low pass filter. They have given the low pass filter specifications. By using these specifications, we have to design the low pass filter and low pass to high pass filter, low pass to band pass filter, and low pass to band stop filter. Okay, so first, if you are seeing this one only, we will get some some questions such as, is it possible? For example, if it is possible, right, how it is possible? So we will arise some curiosity, right? So we will discuss it is possible. Okay, so by using the low pass filter specifications, we can easily transform, or we can easily design the other filters such as high pass, band pass, and band stop filters. Okay, we have some steps, we have to follow those steps, and we can possible to design the other types of filters using the frequency transformation. But those filters are in analog domain. Okay, so in this video we will discuss the frequency transformation low pass to high pass, how to do this. Okay, from the exam point of view, usually they will ask the question from this, design high pass using the low pass filter specification. Okay, so we will see this one problem. Okay, so you know that what is this, what type of frequency transform or frequency response? It is actually magnitude response. These two are magnitude response. This is the magnitude response of low pass filter. This is the magnitude response of high pass filter, right? This is the high pass filter magnitude response. This is the low pass filter magnitude response. You know very well. So by using this low pass filter, we are transforming low pass filter to high pass filter magnitude response, or we are going to design the high pass filter transfer function. Okay, using low pass filter specification. That is very important point. Okay, this is the pass band. Okay, this is the pass band, or we can also say this one as a, this is pass band frequency or cutoff frequency. So this is the stop band frequency. This is the analog frequency. These two are what? Analog frequency. Here we are discussing the analog filter design, right? So we are designing the filter in analog domain in another way. Okay, so all the frequencies should be in the analog, right, in radian per second. It should not be in hertz. Okay, what is this y-axis? Y-axis is magnitude. This is the pass band magnitude. This is our attenuation, pass band attenuation. This is the stop band attenuation. These are should be in the decibel. Okay, so highest magnitude is 1, right, 1 decibel, right? This is the equation we are using for to describe the pass band attenuation. This is the stop band attenuation. Just we are transforming this low pass magnitude response to high pass magnitude response, right? If we are placing some mirror in front of this frequency response or magnitude response, we will see this figure, right? This is the magnitude response of high pass filter. Here the attenuation should be the same. This is the pass band attenuation, this is the stop band attenuation, right? So only that cutoff frequency and stop band frequency, these two frequencies are going to be changed. Okay, so here our cutoff frequency is here, right? For example, you can take this one as a cutoff frequency is 500, right, radian per second, and stop band analog frequency radian per second is 1000. Okay, so if you are transforming into the magnitude response, high pass filter magnitude response, this cutoff frequency or pass band frequency becomes stop band frequency. This is 500, right? And this stop band frequency becomes cutoff frequency 1000 radian per second. This is 500 radian per second. This one is 1000 radian per second. Only the frequencies are going to be swapped, right? But the attenuation, that pass band attenuation, stop band attenuation should be the same, right? This is the high pass filter pass band attenuation, high pass filter stop band attenuation, isn't it? So only the frequencies are going to be changed. Okay, we will discuss one problem based on this. Okay, so here this is one problem. Okay, for the given specification, pass band attenuation is 3 decibel, stop band attenuation is 15 decibel, right? So these are in, usually it is a negative sign. Okay, while using in the, while solving the problem, we are using only positive values. We are not going to use negative values. Okay, so pass band analog frequency 1000 radian per second, stop band analog frequency 500 radian per second. So here we should have to design, we are going to be a design a high pass filter. Okay, using a, this is a low pass filter specifications. Okay, so first step is we have to design a normalized low pass filter. Here they have given only the specifications, right? First we have to design the normalized low pass filter. Second step is using a suitable transformation, right? To get the, we have to use the suitable transformation in order to get the transfer function of a high pass filter. Okay, these are the two steps we are going to be used in order to design high pass filter from the low pass filter specification. Okay, so as I discussed it before, right? So for low, this is the low pass filter specification, this is the cutoff frequency, this is the stop band frequency. Just these two frequencies just changed in the high pass filter. The cutoff frequency here, it becomes 1000 radian per second. Stop band frequency, analog frequency becomes 500 radian per second. See here. So this is our low pass filter magnitude response. This is the high pass filter magnitude response. Again, I am not going to discuss this one. Already I have discussed it. Okay, now just we will discuss how to design the high pass filter transfer function, right? So we know that this equation, so we have already discussed it. Okay, n is the order of the filter. First we have to find out the order of the filter. So logarithm of lambda divided by epsilon divided by logarithm of 1 divided by k. So first we have to find out lambda, then epsilon using these two equations or formula. Okay, so we know that the stop band attenuation and pass band attenuations, right? So they have given in the problem. So pass band attenuation is 3 decibel, stop band attenuation is 15 decibel. You have to substitute those two values in this equation. Then using the calculator, find out the value of lambda and epsilon. So I got a lambda value 5.533 and epsilon value 0.997. Approximately it equals to 1. Okay. Then afterwards we have to find out the another value k. K is the ratio of pass band frequency divided by stop band frequency. 500 divided by 1000, right? The stop band frequencies, because here we are going to design the first low pass filter, right? Then only we are using the transformation, we are find outing the high pass filter transfer function, right? So the pass band attenuation is 500, sorry, frequency is 500, stop band frequency is 1000. So the k value is 0.5, right? So thereafter these values we have to substitute in this equation. N is equal to log lambda divided by epsilon divided by log 1 divided by k. So thereafter we will get the n value 2.468. Usually we have to increase the value of n to the highest integer value. Here we got 2.468. The order of the filter is n is equal to 3. So you know that the transfer function, analog transfer function, right? So this is the analog transfer function of low pass filter, right? So H of S for this is a normalized cutoff frequency 1 radian per second and n is equal to 3 is how we got this. We know these things rules, right? The numerator is always 1 divided by denominator. How I got this denominator polynomial equation? You have to memorize this. For n is equal to 3, see here, for n is equal to 3, the denominator of transfer function h of s is s plus 1 of s square plus s plus 1. I have used that one only. Okay, see here, s plus 1 of s square plus s plus 1, right? This is our low pass filter analog transfer function. Now I have to change this one in as a high pass filter transfer function. So here the cutoff frequency now it becomes 1000 radian per second, right? So actually this is the stop band frequency, analog frequency in our low pass filter, right? So it becomes in the high pass filter as a, it is a pass band frequency or cutoff frequency 1000 radian per second. So we know that this equation, so in order to convert, so low pass to high pass, the first step is we have to use this cutoff frequency. Usually in the previous problems we have to find out this cutoff frequency. Now no need to find out this cutoff, they have given in the problem itself, right? The cutoff frequency, just we have to transform, right? So there in the low pass to high pass, so here the cutoff frequency is 1000 radian per second. Just you have to substitute in this equation. S tends to, in this condition, S tends to cutoff frequency divided by S, 1000 divided by S. Then you have to substitute wherever we have the S value in this equation, right? You have to replace cutoff frequency divided by S, right? 1000 divided by S. Thereafter, you have to simplify this equation, right? So finally, you will get this equation. Okay, this is the transfer function H of S. This is the transfer function of high pass filter. Now we have transformed low pass filter to high pass filter. Here we have defined the transfer function of high pass filter from the low pass filter transfer function. See how it is very easy, right? Only by using the low pass filter specification, first we have find out the analog transfer function of low pass filter. Then we have transformed that analog low pass filter transfer function to analog high pass filter transfer function. Right? It is very, very curious and also uh, very interesting topic also, right? Using low pass filter specification, we can easily find out the transfer function of high pass filter, right? So this is your final result. Okay. We will see other transformation in the next video. Hope you will understand this problem. If you like this video, kindly subscribe my channel, share my channel with your friends, and like my videos. Thank you very much. We will see a very interesting topic with some problems in the next video. Bye bye.